The next speaker is Pramod Padmanabhan. His talk, Groupoid Toric codes, examples of 2D Fracton phases.
Okay, so I would like to thank the organizers for organizing a interesting conference. And I also want to thank Pal, my advisor, for coming all the way to India, because if this was happening elsewhere, I wouldn't have been able to go. Okay, so I will be talking about some work which we did last year. Uh, So this work was with my friend in IIT Bhubaneswar, Indrajit. So I also want to acknowledge Paolo, who is also a student of Bal, but he's not here. So I want to acknowledge him because these are some of the things which I studied from him, which I learned from him, even though he's not involved in this work. But they are inspired by my interactions with him. Okay, so let me start. So as Andres was saying in the previous talk, Kitaev has several examples of topological phases, and Andres was speaking about one of them. So I'm going to talk about another example, which is known as the Toric code. Okay, and so the outline, I will start with the original Toric code as defined by Kitaev. Okay, and that model is for a finite group. Okay, so I will be presenting it like a spin model. Okay, like even though this model it can be obtained from high energy physics also, especially planar gauge theory. However, I will be showing it as a spin model, and you will be able to make the connections to planar gauge theory soon. Okay, as I show you the expressions. So I'll start with this Toric code for a finite group, even though it can be extended for other more general structures. Okay, and then I will explain. I'll be highlighting the features of this model for the simplest finite group, which is C2. Okay, so I'm not going to go into too many mathematical details. I'll just give you the main features. Okay. And then I will explain the work which we are doing. Okay, even though Pal is quite critical about this work, I'll try to explain why I'm going to change this group. Instead of a group, I'll put a groupoid. So I will start by explaining what a groupoid is and how it is going to change the features of the original Toric code. Okay, so this is going to be my outline. So I'm not going to go into too many details. I'll just give you the main ideas. As I have been listening also in the audience for so long, it's very hard to follow all talks like all through the 40 minutes. So I'll try to keep it very simple. Okay. Okay. So I'll start with the Toric code on a finite for a finite group. Okay. So I will start with the ingredients for the Toric code model. So the ingredients include. So as I was saying, it's like a spin model. So I'll start with a lattice. Okay, so the lattice is going to triangulate a two-dimensional surface, and this lattice, like each edge in the lattice, will have will be oriented. Okay, so it is the same as you would do in some lattice gauge theory. Okay, and then for the Hilbert space, I will choose some finite group G. Okay, choose a finite group G, and then choose the group algebra of G. Okay, so this group algebra is going to be spanned by the elements of this group. Remember, it's a finite group, so the order of the group will be the dimension, and it's going to be located on every edge, okay, of this triangulation. So if I call the order of G as this, the full Hilbert space is just the tensor product of the CG on all the edges. Okay, so on every edge, I have these operators. Okay, so if G is an element of the group, you define the action on some other element of the group, which is located on the edge, the left action and the right action. Okay, so this G is just going to act from the left hand side, and over here the G will act from the other side, the right hand side. Okay, so with these so with this input, you will be able to define some operators, which are essentially local operators. So I am showing it to you on a square lattice for simplicity. However, it's true for any lattice. Okay, so I'll start with an operator which I call AVG. Okay, so the G is an element of a group, and the V is the vertex of the square lattice. So all the edges which are around this vertex, they all have some orientation. And if I consider the elements, the group elements like H1, H2, H3, H4, so for every arrow going into the vertex, it will act from the right-hand side with an inverse. And for every arrow which is going out of the vertex, it will act from the left-hand side. Okay, so I'll call this operator as AVG. So in some sense, this is like a gauge transformation. Okay, so this AVG, I will form another operator out of these AVGs, which I call AV. So I have a small typo here. It should be a sum over the elements G. Okay, so I will take a group average of such operators. Okay, and so clearly as it's a group average, this operator AV is a projector. Okay, so if you square it, you will get back AV. Okay, and in the same vein, I'll define another operator which I call the flux operator. Okay, so it locally measures the flux across a phase. Okay, so if I'm going to take the square lattice, and if I have a square face, so I will start from here, and then I'll move in a clockwise direction, and I'll measure the flux. So essentially, I will be multiplying the elements of, I'll be multiplying the elements which are located on these edges. So which is just H1, H2, and if I'm going to move in the opposite direction of in the way the edge is oriented, I'll take the inverse. Okay, and after measuring them or computing this flux, I will check if it's getting projected to the identity element, which I show here by E. Okay, in the same way, I can define other flux operators which project to other elements of the group. Okay, and so by construction, this BF is also a projector. Okay, and this it is not hard to show that this AVG and this flux operator, they will commute. Okay, they'll commute if like V and F are adjacent. Okay, so since I'm working in a two-dimensional space, like every vertex, so the phase operator and the vertex operator, the common support are these two edges. So if I consider a phase over here, for example, okay, so this Hamiltonian which we find here is an exactly solvable Hamiltonian, like just by virtue of the facts which I stated now, which is that these operators, they commute with each other and they are all projectors. Okay, so the eigenvalues, so the complete spectrum is easily obtained. Okay, so for example, the ground state of the system is obtained when is the state which is left invariant by all these operators. Okay, so if I specialize to this to the case when the finite group is C2, okay, as I told you, it's an exactly solvable Hamiltonian. Okay, you will find on a closed surface the ground state degeneracy is a topological invariant. Okay, and the topological invariant is the number of holes or the genus of the surface. Okay, and the other point about the Toric code is the fact that the excitations in this system, which can also be easily obtained, they are deconfined in the sense that they are free to move around in this two-dimensional space. So if I create a pair of excitations, the pair will be connected by a string operator, and that string, it can take any shape or form. Okay, I'm free to extend that string and still have the same energy level. Okay, so now I'm going to show you this other model which is based on these groupoid, in which I change all these features, okay? So the Toric code, like effectively it is described by some topological field theory at the ground space level, okay? But now I'm going to show you how I can change these features by changing the group to a groupoid, okay? So I will be showing you an example of what is known like these days as a Fracton phase, which is characterized by the fact that this ground state degeneracy will no longer be an invariant like this, but it will become extensive. Okay, so I will show you that, and I will also show you that so as a consequence of this becoming extensive, these excitations are also not free to move. Okay, so I will show how all these things emerge. Okay, so I will start by explaining what is a groupoid. Okay, so there are many examples of groupoids, but however, I will just show you the simplest one. Okay, so the groupoid is it's a category. Okay, so like any category is made up of some objects and morphisms. Okay, so an example of a category is the category of sets. Okay, so in which all the object is some set. Okay, and the morphisms are functions between these sets. Okay, however, in a groupoid is an example of a small category in which the objects are they are just some natural numbers. Okay, so I'm going to call this object 1 and 2. Okay, so this 1 and 2, it does not have any more structure. Okay, and then I'm going to take some morphisms in between these objects. Okay, so the groupoid is special in the case that every morphism it'll also have an inverse. So so over here it is illustrated by the following fact. If I take the objects 1 and 2 and consider morphism A, then I should also have a morphism which is going to go from 2 which is going to go in the opposite way, which I call A inverse. So I just change the direction of this arrow over here. Okay, and then I consider other morphisms in which like I'm going to go from 1 to 1 itself and 2 to 2 itself. Okay, so each of these morphisms from the figure is very clear that each morphism will have a source and a target. Okay, so the source of A, for example, is the object 1, and the target of A is 2. And the source of, say, 1, 2, and the target of 1, 2 is going to be the same, and that is 2. Okay, so on this, I can define some composition rules of how to compose two morphisms. And it is actually very intuitive from this figure that if I want to compose, say, A and A inverse, I can start from A and then just follow these arrows and then end up with something. Okay, so if I compose A and A inverse, I'm going to end up with another morphism. It's of course closed under this rule. So I'm going to end up with another morphism in which the source and target has to be this, the object 1. And I only have a single choice for that, which is 1, 1. Okay, so in the same way, I can follow I can do other things. If I do A inverse times A, I will get like the morphism 1, 2. And if I do A times 1, 2, I'll get A itself. However, there are some cases which I cannot compose. So for example, I cannot compose A with A itself. Okay, or I cannot compose 1, 1 with A inverse. Okay, so over here, you're seeing the first difference with respect to a finite group. Okay, so which is the fact that in a group I can multiply all elements, but here I am not allowed to do that. Okay, so I can also I can map all these morphisms to another set of elements which form a semi-group. Okay, so if I consider the morphism 1, 1, the object and the source and target are the same, so I will just call that as x11. Okay, so if I have xij, I is like the source and j is the target. Okay, so if I consider my morphisms as xij, So the composition raw will become obvious from here, because if I do xi1, i2 times j1, j2, then I can only compose them if the target of this guy is the same as the source of this. So that means I2 has to be equal to J1, okay? And then I can compose them, okay? However, so I'm not going to show you any other example. I will only work with this simple example to show the features, okay? Okay. So now the group algebra is going to get replaced with this groupoid algebra. Okay. So unlike the group, so it is a non-abelian thing by construction. Okay. And so in this example, I have 4 elements. So on every edge, I'll put this C4. Okay. It is spanned by the morphisms of this groupoid. Okay, and in fact, this groupoid has the structure of a Weak-Hoff algebra. But I'm not going to use this immediately. But however, I'll say something about this in the end. Okay, so therefore, now I'm going to remove the phi's over here to simplify the notation, and I will say that the local Hilbert space on every edge is spanned by these 4 elements. Okay, this 1, 1, 1, 2, A and A inverse. Okay, so here I also want to make a quick remark about the groupoid structure, which is the fact that this 1, 1 and 1, 2, in some sense, they are like the identities. Okay, so if a group has a single identity, the groupoid has several identities. So they are like partial identities. Okay, so if you want to get the full identity on the groupoid, I need to add all these partial identities. Okay, so the total Hilbert...
Pramod,
yes.
I just want to ask you one question.
Yeah.
The group algebra that you introduced, what is the underlying group? What is the underlying group?
I mean, so in the first case, it is any group.
In this particular example.
No, so in this example, there is no group at all.
Then how can you have group algebra?
No, this is not a group algebra. This is a groupoid algebra. I mean, I will tell you some more. You will see. I'll show you another one example, okay? Okay, so the total Hilbert space is just a tensor product of these C4s on all these edges, okay? So now again, on each edge, I have a local operator, okay? And these local operators will have a left or a right action. However, so in this case, I will not always have a non-zero action. It's because I have to make sure that the target of this G is going to be equal to the source of this H. Otherwise, I will get something 0. Okay, so it is the difference between the group and the groupoid. Okay, so over here I've just given some examples which is going to illustrate this fact. So I'm not going to go over them. Okay, so now I'll tell you the main difference from the group case. Okay, so if I try to construct similar operators like these AV operators as how it was done for the case of the finite group, if I do the same thing for the groupoid case, I will get such operators. Okay, so so here I'm showing you a vertex which only has 2 edges, and one of it is going in, the other is going out. Okay, so again, it is some kind of a groupoid average. Okay, so such a groupoid averaging is again going to give me a projector. Okay, however, now in the group case, you can construct orthogonal projectors to a given projector. But in this case, I will have more such orthogonal projectors. So I will have, so in particular, I'll have examples of projectors which project to spaces in which the source the target over here will not match the source over here. Okay, so if I have a 1, 1 on the edge which is going into the vertex, I can have a 1, 2 which is a morphism whose source and target will not coincide with 1, 1 on the other edge. Okay, so I will get such extra operators which are orthogonal to the original groupoid averaged operator. So it is a key difference between the group case and the groupoid case, and it is also the origin for the Fracton phases, which I will be showing you soon. Okay. Yeah, so the same thing I can do for the phase operators. So again, like over here, I have showed you an example of a two-edged phase. So I have an edge over here and I have an edge over here. Okay. So suppose if I want to project to the one element, the morphism which is labeled by 1, I have to consider all the ways in which I can obtain the flux of 1. So if I multiply a 1 with 1, I'll get 1, of course. If I multiply A with A inverse, I will get 1. On the other hand, if I multiply A inverse with A, I'll get 1, 2. Okay, and so on. So I can get all these different fluxes. Okay, I can project to the 4 different morphisms of this simple example. However, if I add these 4 operators, which are all orthogonal to each other, and by construction they are projectors, I will not get the identity. Okay, if you want to get the identity, I have to include this other projector, which will project to the zero flux. Okay, so it will include all those configurations which if you multiply, which cannot be multiplied in the groupoid algebra. Okay, so for example, I cannot multiply the 1 with A inverse. So it will contribute to the 0 flux and so on. I cannot multiply an A with an A or a 1, 2 with a 1, 1 because their sources and targets are not compatible. Okay, so therefore, unlike the finite group case, you have a new operator here. Okay, so which appears both in the vertex and in the phase operators. Okay, so I need to add this BF0 operator if I want to span the full Hilbert space. Okay, so in fact, if you so it's easy to show that this groupoid averaged operator is going to commute with the flux which projects to the full identity, which is the sum over the partial identities. Okay, so suppose if I construct a Toric code kind of example, if I construct a Hamiltonian out of these AV zeros and this BF11 plus BF12, I will have a model which is very similar to the group Toric code. But in this model, you will only find a single ground state. Okay, like irrespective of the topology of the surface, you will only find a single ground state, and all the excitations are frozen. Okay, like they are not free to move at all. Okay. However, I will show you other examples now in which these other features will start to appear. Okay. So the first thing which I want to do is as I was saying you, the groupoid algebra is a non-abelian structure, and it is very hard to solve it if you analyze the problem as a non-abelian model. Okay. So the first thing I will do is I will translate this system into an abelian system. Okay, so I'm going to show you how I'll achieve that. Okay, so if I take any oriented edge, I am allowed to have like any of these 4 morphisms, which is 1, 1, 1, 2, A or A inverse. Okay, but however, if I have 1, 1 from here, I have a natural way to map it to another space. Okay, in which instead of using the morphisms, I will use the object index. Okay, so the 1, 1 over here is the same as using like object index 1 and 1 over here, and 1, 2 is the same as using the object index 2 and 2. Okay, and A is 1, 2 and A inverse is 2, 1. So therefore, this space, this local Hilbert space, which was a C4, it can be mapped into a tensor product of 2 C2s. Okay, so on every edge, I will put at the 2 endpoints of the edge a C2. Okay, a C2 here, a C2 here, and the C2 is spanned by the object indices now. So I have essentially converted this model, the non-abelian model, into a kind of a qubit system. Okay. So if you do this, the square lattice which we started with, which is oriented, like every edge has an orientation here. So around each vertex, I have to put a qubit space. So each vertex will get expanded to a square like this. Okay, if I expand each vertex to a square, I will get I'll get a lattice like this, which is known as the Square-Octagon lattice. Okay, so the full Hilbert space will get mapped to something like this. Okay, as I just explained. Okay, so if I do this, I can map all the operators now, all those 4-dimensional operators. Okay, the morphism, the left action of a morphism on an edge, it can be mapped to an equivalent operator acting on the qubit space. Okay, so I have something for the left action, and similarly I'll have something for the right action. Okay, so everything else is details. I'm just glossing over those parts. Okay, so if I continue doing this, I can like write down the groupoid averaged operator in terms of the C2 space. Okay, so now it will look very similar to the all these abelian toric code examples. Okay, so essentially the first operator here is the operator which also appears in the group toric code. Okay, and all the other operators here, it's some kind of a check operator. Okay, so if I take a vertex, I have 4 corners over here, so I have to check if these two, if each corner is either a matched configuration or a mismatched configuration. Okay, so if Z and Z, if in this corner, if I have the same index, which can be either 1, 1 or 2, 2, so I will get a +1 eigenvalue here, and this projector will be non-zero. So I can do the same thing for every corner. Okay, so such an operator will only act if the configuration around a vertex is the same. Okay, so which is essentially explained, which is illustrated over here. So the groupoid averaged operator will only act on such configurations. All these other operators which we appear is an artifact of the fact that we are using groupoids. Okay, so they will act on operators, they will act on states in which you have at least one mismatch in some corner around a vertex. It is something which does not appear in the case of the finite groups. Okay, of course, so it is going to change according to what lattice which you have. Okay, so I'm only showing you for the square lattice. Okay, so the same way I can also compute the flux around a phase in this qubit, in the qubit formalism. Okay, so if I take a phase F over here, a square phase, I have 3 corners over here. Okay, I can only multiply the groupoid configuration, the morphisms on these 4 edges, if I have the same configuration on these 3 edges. Okay, so I'm going to measure the configuration across these 3 corners with the help of such an operator. Okay, so if you do this, we can construct the projector to 1, 1, which is the morphism 1, 1, and similarly all the other morphisms. And we also have this special guy, which is the projector which projects to the zero flux. Okay, so now I'll show you the example. Okay, so I can actually construct several examples from all the operators I have shown you. Okay, but I will show you one particular example. Okay, so I will take some Hamiltonian which looks exactly like the toric code Hamiltonian. So again, it's going to be exactly solvable. They are projectors. They all commute with each other. Okay, so this vertex operator will be similar to the toric code one, except that it will only act if there is a mismatch across the northeastern corner of this vertex. Okay, and the phase operator will only act if there is an overall mismatch, okay, across a phase. So if you do this,
Pramod,
yeah,
10 minutes more.
Yeah, I'll finish. Okay, yeah. So suppose if you do this, we can find how many ground states are there, and you will find an extensive number over here. Okay, your NV is the total number of vertices. Okay, so over here I have a factor of 2, an overall factor of 2, and 2 power NV. Okay, so now I have to try and construct the operators which will produce these ground states. Okay, so the first global factor is going to come from a global symmetry. Okay, so there's a global symmetry operator, and it's going to, so for every state I construct, I can always construct another state which is which actually form two different superselection sectors because they are separated by an infinite energy barrier. Okay, but however, the other factor of 2 power NV, they arise from some kind of loop operators. And these loop operators are going to be constructed out of these 4 configurations. So I'm not going to go into the details, I'll just start showing you the final answers. So every loop, like whether it's contractible or non-contractible, is going to give you a new state. So unlike the original Toric code in the finite group case, in which I only get new states from non-contractible loops, in this example, you will get a new state for every loop, which is contractible also. Okay, so the main reason for this is the fact that these loops, which in the Toric code, you can move these loops around. Okay, but in this case, in the Groupoid case, these loops are very rigid. I cannot move, I cannot shift this loop to another a contractible loop which is translated. I cannot do that over here. Okay, and all this is coming due to the fact that we have changed the group to a groupoid. So here I have shown you an example of a state coming from a contractible loop, and here is an example which comes from a non-contractible loop. Okay, so if I change the non-contractible loop, if I deform it, I will get a new state, and it is going to be equal to a contractible loop, a contractible loop here times a non-contractible loop. The only amount of deformation which I'm allowed to do is a very local one. I can only deform this loop around the vertex which is adjacent to it. I cannot do any more deformations. So each non-contractible loop which can be formed across this surface will give you a new state. Okay, and I will show you the construction of the ground state also. Okay, but Sanatan already told me that I shouldn't make it too late, and I have already made it late. So I think I'll skip this part. Okay, so I will just go to the fluxes. Okay, so suppose if you consider the excitations in this model, if I cut open any of those contractible loops, I will get an excitation. Okay, I'll get a pair of excitations which I'm showing here by F1 and F2. So I have excited 2 fluxes over here. However, in the Toric code case, such excitations are completely free to move. But in this example, they are not fully free to move. So I can only move freely as long as I move in the southern direction of a vertex or the west of a vertex. But as soon as I try to move, if I try to break this rule, and if I move in the east or the north, I will start seeing some more energy. So the fluxes are free to move in one side, but on the other side they are confined. Okay, which is very typical of these Fracton phases. Okay, so I have showed you this example of how a Fracton phase can emerge in a 2-dimensional setting with just using simple gauge theory. I have just replaced the finite group with a groupoid. Okay, so as a I'll just flash this example. So if I consider another example in which I have the same kind of groupoid, except now that the morphisms, they're going to take another degree of freedom, which is like a color degree of freedom. Okay, so I have the same 2 objects now, but however I have increased the number of morphisms. Now on the color index, it's like a group. It's because I can multiply the 2 colors. If I multiply a blue and a blue, I'll get a blue. But if I multiply a blue and a red, I'll get a red. So there's some kind of a Z2 structure on the color index. So if you construct the same model with a groupoid like this, you will in fact find an example in which both the fractonic phase and the topological phase, they'll coexist, okay? And in fact, something which is interesting is that you will see that the fractonic excitations over here, they are confined into this into the topological excitation, which means if I try to do only a fractonic excitation, it won't be free to move. But as soon as I combine two fractonic excitations, it will become a topological excitation and it will become free to move. So this is something very similar to like what happens in quarks, maybe. Okay. So as promised, I will stop after just making a few comments. So I have showed you examples of this fracton phases in 2 dimensions. So here I give you some perspective that almost all the fracton phases which people have seen in the literature, it started with 3 dimensions. Okay, so here I'm showing you some examples of stable ones. I didn't talk about the stability here, but it's possible to show that it is also stable, that the stable ones are emerging even in 2-dimensional systems. Okay, and I'm showing you that the groupoid algebras that we have is like a rich playground for constructing such exotic phases. Okay, so in fact, so this is the answer to Pal's criticism is the fact that this so the reason why we consider these groupoids is that this groupoid is a simple example of what is known as a multifusion category. Okay, so such things have been the inputs to construct these other kind of exotic phases called string net phases. Okay, so they generalize the topological phases of Kitaev. Okay, yeah. So finally, I want to. So in fact, if you look at the literature in all the other string net models, they don't consider this. The zero flux. So they are not considering the exam. So they call the physical Hilbert space as only those states in which I can compose the morphisms. So they are throwing away these other states. But if you don't throw them away, if you consider them, I just showed you that you will find these exotic phases. Okay, and finally, the main reason why Kitaev's model was introduced was because they actually provide a way to do quantum computing in a fault-tolerant way. Okay, so these topological codes, they find their major use in the hope that there will be a quantum computer built with the help of these kind of examples. Okay, but however, if you take a Toric code model on a surface, on a torus, you can only encode 2 logical qubits in such examples. Okay, so you cannot do large-scale quantum computing with them. But with this fracton phase, I just showed you that every contractible loop will give you a new state. Okay, so I can encode far more number of qubits in such examples. Okay, so which is another reason why we are considering these systems. So I think I'll stop there. I want to say happy birthday to Bal. Okay.
So any question?
Thanks, Pramod. It's a wonderful talk. Very nice. Definitely, Matt side, I think it's beautiful. Okay. My trouble with these models, also with Paulo, is that I don't know how to realize it in the lab. So I'm blocked there. What do I do with this? Okay? This I am not very clear yet. But clearly, mathematically, it's very rich model, I should say. Okay? Thanks again. We'll talk later.
I will take you to Sangeeta many times, don't worry.
Okay.
And you'll change your opinion.
Okay, we'll talk later about all this.
Sure.
You're here, so.